Oh, very well. We are pleased to have today the colloquium Eran Assaf from Dartmouth College, and he will speak about lattice methods for modular forms. The stage is yours.
Thank you, Ron. I'd like to thank the organizers for letting me speak here in the colloquium, also in this time, which might be not extremely convenient for all of you. So thank you for coming. And I know this is a difficult time in general. I hope everyone is well and that things will get better. But let me go back to talk about lattice methods for modular forms. So I do number theory, and number theory we care about, well, things like the integers and rationals, and maybe very classical question that one can ask, for example, in this context, is the question of representation numbers. So if we have some quadratic form with integer coefficients, and throughout my talk, all the quadratic forms will be positive definite. Then we can talk about the representation numbers of these quadratic forms. So in how many ways can we represent a number using this quadratic form? How many solutions does this equation have in integers? This is a very classical question, very arithmetic in nature. And well, this is not a very well-defined question. We can try to refine it slightly. When we ask what is the number, or we want to count, we want to ask, is there a nice formula for this number? And again, nice is not a very well-defined notion, but we want to express it in terms of other things that we know and care about. So what is an example of a nice formula? So let's start with this very classical example of Jacobi. If we're looking just at the sum of 4 squares, then there's a very nice formula. Everyone would agree. Just sum over all the divisors of the number that are not divisible by 4 and multiply by 8. Let's just check a few numbers to see that it makes sense, right? If we're looking at the numbers of way to represent 1, then we have 4 places to choose the 1, and it could be either a plus or a minus 1, so this gives us 8 options. Okay, that seems to agree with the formula, right? It's 4 times 2. And if we want to get to 2, we can only place 2 1s, right? 2 is 1 plus 1 plus 0 plus 0. So now we have 6 ways, right, to choose the 2 places to put the 1s in. And we need to multiply it by 2 options for the sign for each of them. That's 24, which is 8 times 3. So the formula makes sense. And so how does one prove such a formula? That's a good question. I'll show 2 ways. If you search the internet, you'll probably find a million proofs. All of them start with the triple product identity, some weird identity of generating series. Our starting point will be the same. We start with this generating series of representation number. And the point that is slightly obfuscated in all these proofs is that this generating series actually lies, it's very unique, and it lies in a very small vector space. So the idea will be to look at some vector space, which is relatively small, finite dimensional, that this generating series lives in, then find a basis, a nice basis for this vector space that we can represent using other things like sums of divisor, and then just represent this generating series in terms of the basis. Okay, we only need to calculate finitely many coefficients, and then we're done. So this approach is taken in many proofs. Sometimes this finite dimensional vector space is some space of elliptic functions, sometimes some spaces of differentials. The proof that I want to look at is when this space is a space of modular forms. So these are space of modular forms of weight 2 and level 4. And just to make sure we're on the same page and you know what I mean when I write modular forms. So we're looking at the moduli space of elliptic curves. So elliptic curves are solutions to equations looking like a quadratic in one variable is equal to cubic in the other. And in number theory, we care about the integral or rational solutions to these equations. The question of rational solutions is notoriously difficult in general, not for this curve. And the major breakthrough was to understand these things through their complex points, their complex solutions. And over the complex, we have a result of Weierstrass, a complex uniformization, which tells us that every such elliptic curve over the complex number is isomorphic to the quotient of the complex numbers by a lattice. And in fact, one can even choose this lattice so that it's of the form spanned by 1 and z simply by scaling and assume that z is in the upper half plane. Now, naturally, lattices don't change when we change the basis. That gives us an action of SL2Z. And that's why we usually look at this fundamental domain for the action of SL2Z mod H. And modular forms are nice functions on this moduli space. Maybe more concretely, we sometimes want to keep track of more than just the elliptic curve. We want, for example, to keep track of the elliptic curve and some subgroup of order n. And for example, in this parameterization, this will correspond to C mod lambda z and the point 1 over n plus lambda z. So in order for an element of SL2Z to actually preserve, the group generated by this. In order for an element of SL2Z to actually preserve this subgroup, we really want it to be in a slightly smaller subgroup. And these are all matrices such that this bottom lower corner, left bottom corner is divisible by n. So when we have functions on this moduli space, so when we have functions on this moduli space, we call them modular forms. But of course, sometimes we don't want just to look at functions. We want to look at some line bundles on this space, or maybe another way to say it, these are not functions that are functions on the moduli space, but functions of elliptic curves that behave well with respect to isomorphisms, or functions on the space of lattices that behave well with respect to scaling. What do I mean by behave well? Well, I want them to be homogeneous. For example, I want, if I scale my lattice lambda, I want to have a homogeneity property. So this translates, of course, through this action on the upper half plane to a formula that you might have seen many times before. And we say that F is weakly modular of weight K and level N if F of AZ plus B over CZ plus D is CZ plus D to the K times F of Z for all matrices in this group, gamma naught of N. Okay, so basically these are nice functions on the moduli space of elliptic curves. And the only point that I want to make is that here we said weakly, well, what would make them actually modular? Well, this moduli space is not compact, so we usually compactify it, and we want functions on this entire compactified space, which translates to nice growth conditions of these functions. And maybe a nice way to see that is that the matrix 1, 1, 0, 1, which lies in this group inside SL2Z, acts through Z goes to Z plus 1, which tells us that all weakly modular forms are actually Z periodic. So one can always write them. They have a Fourier expansion. Well, one can always write Q expansions like this, where Q is e to the 2 pi I Z. Basically transforming this domain into a puncture disk. Okay, so this will be our relation to generating series that we've seen before. And in the case that we have modular forms, so they are actually functions on the compact space, we really want these Q expansions to be holomorphic. So we want M to be at least 0. So when I write MKN, this is really the space of modular forms of weight K and level N. Okay, I should say that when the level is not trivial, it's not enough to demand that this Q expansion will be holomorphic, will start at 0. There are finitely many cusps that we add, finitely many points that we add to compactify the space, and we need it to be holomorphic at all these points. And our point was that theta of Q was the Q expansion of a form in this space, the space of modular forms of weight 2 and level 4. And it's pretty straightforward to compute the dimension of the space. It's only 2-dimensional, and one can actually find a very nice basis for this space, which has as coefficients of the Q expansion these sums of divisor functions. And that's how one can prove Jacobi's theorem this way. Okay. Once we've done that, we can ask ourselves, okay, this is sum of 4 squares, but there are many other quadratic forms. How can we do that with other quadratic forms? Well, I'll have to introduce some terminology for dealing with quadratic forms in general, but we will see that kind of the same path works. So we start with some quadratic form over vector space over rationals, and we take an integral lattice inside. So when I say an integral lattice, I mean that the values of the quadratic form are integral. This is sometimes called also even integral lattice. If we write T for the associated bilinear form, then it means that the matrix representing T is always has integral entries, and it has even entries on the diagonal. The discriminant of the lattice is the determinant of these associated bilinear forms up to a factor of 2 if our dimension is odd. The level is the smallest number that if we multiply the inverse of this form by it, we get something integral with even diagonal. And again, we can still take this generating series of representation numbers this time for the number of elements of the lattice that have norm, which is exactly n. And this generating series is again, turns out to be a modular form. It satisfies the transformation properties and the growth conditions that we expect for a modular form. Here I introduced another notation. We have a character here. So that just means that instead of acting through CZ plus D to the K, a matrix ABCD will also act by a character on the bottom right corner. And this character here is a Kronecker character depending on the discriminant of the lattice. Okay. Now, that might look very weird and sound very theoretical, but let's just look at an example. So let's take a three-dimensional vector space with a quadratic form x squared plus y squared plus yz plus 3z squared. And our lattice will just be the standard lattice. So writing in the standard basis the Gram matrix, the matrix for the associated bilinear form, we get this bilinear form. So it's easy to see that the determinant is 22. So in this case, the discriminant is 11. I'll also note that if we take another basis, of course, we can get another Gram matrix. It will have the same determinant. So for example, if we take 1, 0, 1 to be the first basis vector, we get this Gram matrix. And if we want to compute the level, we need to invert this matrix. And it's quite straightforward to see that the level here is 44, which tells us that this generating series, the representation numbers of this quadratic form, gives us a modular form of weight 3/2, level 44, and quadratic character, the Kronecker character at 11. Okay. So again, one can try to find bases for these spaces of modular forms. This one, by the way, is slightly larger. It's also already dimension 5. And try to get some nice formulas this way. Of course, when the dimensions get large, the formulas are not as nice, but one can still obtain many interesting answers from this line of thinking. For example, getting asymptotics for number of representations as sums of squares has been worked out in these cases, and there are also pretty nice formulas for sum of squares up to 12. But this also leads to other questions. So we have this map, we take lattices, and we create their generating series, this theta series. And the question is this map good enough? What does it capture? Or in another word, is it injective? That leads to a very classical question in another field, which is, can you hear the shape of a drum? So before I tell you a little bit about this problem, I should tell you that, of course, this map is clearly not injective, because if we have some linear transformation that preserves the quadratic form, and we map the lattice using this linear transformation, then we didn't change anything, right? All the representation numbers will be the same, generating series will be the same. We call such lattices that are mapped to one another by such a linear transformation isometric, and these linear transformations are called isometry. But okay, we can refine this question and ask, if the theta series are the same, are the lattices isometric? Why is this related to, can you hear the shape of the drum? Well, think of the drum as a manifold, and the things that we hear, the sounds that it produces, are just eigenvalues of a different natural differential operator on this manifold, the Laplacian. Now, a very easy way to construct manifolds from lattices is just to take the corresponding torus, right? We just take Euclidean space, quotient by the lattice. We get an n-dimensional torus, And if it's a Riemannian manifold, as a Riemannian manifold, its Riemannian distance depends on the quadratic form that we have on the lattice. Now, if we look at the dual lattice, so the dual lattice are all the elements that pair to something integral with elements of our lattice, then they give rise to eigenfunctions of this differential operator. This is very simple to see because the Laplacian here is just the usual Laplacian, differentiating twice every variable and summing over all of them. And you could see that the eigenvalues of the Laplacian are just proportional, to the norms of elements in the dual lattice. Okay. So the question of can you hear the shape of a drum is, can you infer from what we hear from the eigenvalues of the Laplacian, can you infer the shape? And of course, if I find two Riemannian manifolds that are non-isometric but have the same eigenvalues for the Laplacian, then I show that there are two drums with different shapes that sound the same. So if you can find two lattices that have the same theta series, then the spectrum of the corresponding Laplacians on the manifolds will be the same. And the answer is still no. And a very famous example one can get looking at dimension 16. So we write dk for the family of lattices of vectors such that sum of all the coordinates is divisible by 2. And we throw in also the vector with all the coordinates 1/2. So when k is divisible by 8, this gives a lattice with discriminant 1. And specifically, we call these lattices EK. It's a very famous family of lattices. And so we see we get both when n equals 8 and n equals 16, we get a discriminant is 1. And we get two lattices, the orthogonal direct sum of E8 plus E8 and E16 itself. They're not isometric, which one needs to work a little bit to show by looking at specific 4-dimensional lattices that are found inside them. But of course, if we use the theta map, we know that we're going to land in this vector space of holomorphic modular forms of weight 8 and level 1. And this vector space has dimension 1, which tells us that these generating series are the same. Okay, so this is a famous example of how you can't hear the shape of a drum. Okay, so we have this theta series map. It gives us some nice information on arithmetic questions. It's not injective. Can we do something better? Well, we could refine this map. And instead of taking one vector, we could take G vectors every time. And we could look at all the ways that these G vectors embed into our lattice. And the thing that's written here is basically the Gram matrix of these G vectors. Now, in order to keep track of all this information, we can't do it with a generating series in one variable anymore. But we can do it by using more variables instead. And these generating series, again, turn out to be modular form. So I already wrote it down here in a way that looks more like what is known as a Siegel modular form. So instead of classifying elliptic curves, they classify their high-dimensional cousins, a billion varieties of higher dimensions. And they are classified by, instead of the upper half plane, by Siegel's upper half space. So these are G by G matrices, which are symmetric and such that the imaginary part is totally positive. And using this parameterization, one can look at this generalized theta function as what is known as Siegel modular forms of degree G. And again, the point of what these spaces classify is not very important at the moment, just that these are well-known finite dimensional vector spaces for which we have formulas for the dimensions. We sometimes can find elements in them in other ways, and these can relate our lattices to other objects. And again, one can ask, is this generalized theta series map, is it injective? In the example we just gave, in fact, it fails to be injective for G equals 2 and 3 as well. And only dimension 4, one actually gets something different. And again, the way to see that it's the same for 2 and 3 follows from dimension calculations. So one can look at the difference between these two theta series, see that it's in some smaller dimension, smaller vector space inside this space of modular forms. For example, when G equals 1, we look only at these modular forms whose first coefficient is 0. And this vector space is trivial for G up to 4. Okay. But as I said, when one goes to G equals 4, one obtains that the theta series are actually distinct. And this is part of a more general theory where for every lattice, one can find some G for which this map is injective. Of course, it doesn't tell us what is this G, and there's still a lot of things to understand here. Now, I want to think of this phenomena of looking at the difference as something slightly different. So instead of looking at the theta series of each of these lattices and then subtracting, I would like to say that I took the difference of these two lattices and I mapped it using the theta series. So I have something in the kernel of this map for G equals 1, 2, 3, but not for G equals 4. That will lead us to the constructions we will see in a bit. That's the idea behind them. And in such case, I want to say that the depth of such a vector is 4. So it's how deep I have to go to actually see this vector when I apply theta map to it. Okay. So I've told you a lot about lattices and theta series, and a little bit about modular forms. But I promised you lattice methods for modular forms. So where do these appear? This is where they come in. So instead of using the theta series to map lattices to spaces of modular forms, I will create a space of modular forms from the lattice itself. And the theta map will be a map between spaces of modular forms. This will be the main idea. So I'll denote by O of V the orthogonal group of the quadratic space, just a linear transformation preserving the quadratic form. And as before, we will say that two lattices are isometric if there is an isometry that sends one to the other. The genus of a lattice will be all the lattices in the vector space that modulo every prime power are isometric to our original lattice. So here it's written in a slightly different language. Instead of looking at modulo every prime power, I'm looking at the completion. So I'm tensoring with ZP, and I'm saying I'm looking at all the lattices that locally everywhere are isometric to our original lattice. And the class set of the lattice are just the isometry classes, global isometry classes of our lattice. So this is really the set measuring the failure of the local to global principle for this quadratic for this lattice. Now, if you are more representation theory and automorphic forms inclined, you might notice that this could be viewed as a double coset space. So if you're looking at the orthogonal group at every prime P, you can form an adelic group. And these are the adelic points of the orthogonal group. This is the OV hat here. And on the right, we quotient by the things that stabilize the lattice. And on the left, we quotient by global isometries. So we really have the rational points of our group on the one hand and some open compact on the other. And the reason that you don't see here a lot of adels and analysis is that our group is a compact group, a compact form. And so we don't really have to deal, all our spectrum, all the representations are discrete. We don't really have to deal with all the complications arising in higher dimensional cases. Okay. So our space of orthogonal modular forms of level lambda or lattice will just be functions on this class set. Okay. So now I can really talk about subtracting two lattices. This is a vector in my vector space, right? It's just the difference between two characteristic functions. And by extending linearly functions on lattices, on isometry classes of lattices, I can get functions on this space of modular forms. Okay, so we get a better question. Is this generalized theta map from the space of orthogonal modular forms to the space of Siegel modular forms injective? So before we give some more data on this, on the properties of this map, we should say that it's not just some random map of vector spaces. It has very nice properties, and these vector spaces have additional structure, and this map intertwines them in a very nice way. So what is the additional structure? So here I come to a very old construction of Kneser from the 50s called p-neighbors. So if we have a lattice in our vector space, we say that it's a p-neighbor of our original lattice lambda, and I'll denote it by tilde p, if it is integral and the index of the intersection in each of the lattices is a p. So if we remember linear algebra and invariant factors, then it means that there's a basis for this lattice such that 1 over p e1, p e2, e3 to en is a basis for this second lattice. Okay. This is, of course, let's assume somewhere that p doesn't divide the discriminant. Otherwise, it might also be true, but there are some other technical conditions that I don't want to get into them. So for primes not dividing the discriminant, in theory of invariant factors just give us the existence of these bases. And it's relatively simple to see that if lambda and pi are p-neighbors, then pi is in the genus of lambda. Well, in every other prime than p, we didn't change the lattice at all. It's just the same lattice, so of course they're isometric. And at the prime p, this construction, these invariant factors, explicitly shows us that this is an isometry. Now, because we know pi is integral, the existence of this basis tells us that this first basis element E1 has to have norm divisible by p squared. Okay, and in fact, using Hensel's lemma, it's easy to see that it gives us a bijection between isotropic lines in lambda mod p and p-neighbors. We just map every p-neighbor to this particular element whose norm is divisible by p. And again, this might sound complicated, but it's very simple to see. For example, if we have a three-dimensional lattice, then our quadratic form is just a conic, right? It's a quadratic form in 3 variables. it's a conic in P2, so it's isomorphic to a projective line over Fp, and as a consequence, it has p+1 elements. Well, this should be D. Okay, let's look, for example, at the quadratic form we looked at before, x squared plus y squared plus yz plus 3z squared. We want to find the two neighbors of our lattice. So we look at the isotropic lines modulo 2. We see that this form is anisotropic modulo 2. So x has to be 1. And every choice of y and z that is not both 0 will give us an isotropic vector. So this gives us these three vectors. And as I said before, using Hen's lemma, we can see that they lift to three vectors that are isotropic modulo 4. Okay, 1, 0, 1, 1, 1, 2, and 1, minus 1, 1. Let's look at the first one of these. Okay, it's an isotropic vector. It will give rise to a two neighbor. We've seen that the Gram matrix with this element as the first element of the basis is the matrix right here. And by taking a two neighbor, we want to divide the first vector by 2 and multiply the second vector by 2. So the effect on the Gram matrix will be to divide the first row and column by 2 and multiply the second row and column by 2. And it will give us this new Gram matrix of our two neighbor, the one that we see here. And it's an easy exercise to see that this has another basis in which the matrix looks like the one on the right. Now, I claim that this lattice is not isometric to the lattice we started with. One can see this, for example, by counting the number of vectors of norm 1. This 2 by 2 submatrix shows us that here there are 6 vectors of norm 1, and in the lattice we started with, there are only 4. Now, what does it tell us? So we started with some lattice, this lambda 1. We took a two neighbor using an isotropic vector mod 2, and we ended up with a different lattice, which is not isometric to the one we started with. Now we can do the same for the other neighbors, right? For 1, 1, 0, we will end up with a lattice which is isometric to the thing we started with. And for the 1, 1, 1, we will get again a lattice isometric to the second class. We could also start with this lattice and look at its 3 two neighbors and see which isometry classes are we landing in. And we will see that all 3 of them give us lattices that are isometric to lambda 1. Now you can see that this graph that I just drew is 3 regular, and that's not a coincidence. In general, we could play this game for any prime P and for any class set. And this gives us very nice graphs. They are Ramanujan graphs when k equals 3 and almost Ramanujan in a way that can be made precise in higher dimensions. And more than just these graphs, we can form their adjacency matrices, right? So I wrote here T2 for the adjacency matrix of the graph that we see here, right? We have 1, 2, 3, 0. And similarly, one can repeat the thing for p equals 3 or p equals 5 and get the other matrices that we see here. And you can see that the sum of the rows is always p plus 1, right? Here it's 3, here it's 4, here it's 6. But these operators actually commute, and they're also self-adjoint with respect to a to a natural with respect to a natural inner product. One has just to take into account the automorphisms of each of these lattices. And this gives us a notion of a Hecke operator on this space of modular forms. And the Hecke operator is just acting on a function by summing over all the p neighbors. And again, if we replace the function by the characteristic function of a lattice, then we get these adjacency matrices. And since these operators commutants are self-adjoint, then it tells us that there is a simultaneous basis of eigenvectors, and these are eigenforms. And in the example above, we can see that other than the obvious eigenform 1, 1, we have 2 minus 3 as an eigenform, because, for example, 1, 2, 3, 0 times 2 minus 3 gives us minus 4, 6, with eigenvalue of minus 2. Okay, and for all primes that are not 11, we see that, well, this first trivial eigenform always has eigenvalue of p plus 1, and the second has an eigenvalue which is some numbers AP, where these APs are, well, A2 is minus 2, A3 is minus 1, A5 is 1, and so forth. And if you've been doing it long enough, you'll recognize them as the coefficients of a Q expansion of a modular form of weight 2 and level 11. Note that this is not of weight 3/2, like we get after using theta series. Another way to think about this sequence of numbers is to use modularity. So if we look at this elliptic curve that I told you about before, then these numbers are just p plus 1 minus the number of points on this elliptic curve modulo p, for all p different than 11. Here's a different example. In our friend from before, the rank 16 lattice with discriminant 1, one can look at this other eigenvector, phi here, and notice that it satisfies this equation. Now here, tau is Ramanujan tau's function. So it comes from, it's the unique modular form, which is cuspidal of weight 12 and level 1. And maybe I should say that in both these cases, I didn't really prove to you that this is what happens. I've only shown you some numbers and told you that they match. These are actual facts one can prove, as I will tell you briefly. So first, for this exceptional star here that we got a different weight and level. So this is an example of an exceptional isomorphism. We're looking at the orthogonal group on 3-dimensional space. And its Lie group SO3 is isomorphic to the Lie group SL2. These are just B1 equals A1. They're both just a point in the Dinking diagram. So modular forms for these two groups are the same. And we're looking at a compact form. So there's some transfer that one needs to do. But it's the theorem of Birch, Hein, Tornerier, and Voigt that for rank 3 lattices, one can make this very precise. And for example, if the discriminant is square free, you really get a Hecke equivariant injection from orthogonal modular forms for this lattice lambda to classical modular forms of level corresponding to the discriminant. And they explicitly describe the image. Now, one can do even more. There are other exceptional isomorphisms. However, if one wants to be really general and do things over arbitrary base fields, there are many things one has to take into account. Even this theorem, if you look at its statement, it's quite longer and it involves a lot of actions, a lot of things acting on these spaces that I will not go into. But for example, if we go to the next level for dimension 4, then the orthogonal group of dimension 4, SO4, is isomorphic to SL2 cross SL2. Here it's just 2 points. D2 is A1 cross A1. And this gives us a theorem in a joint work with Fretwell, Ingalls, Logan, Secker, and Voigt, that tells us that under some technical hypothesis on our lattice lambda, if we let F be the quadratic étale algebra over Q, whose discriminant is the discriminant of the lattice, then we can get a Hecke equivariant injection from the space of orthogonal modular forms for this four-dimensional lattice to a space of what is known as Hilbert modular forms. And these classify, instead of elliptic curves, they classify a billion surfaces with real multiplication over this real quadratic field. Again, this is some nice moduli space, and these functions have nice properties. And another thing that's slightly different here is that this space has an action of the Galois group of this quadratic étale algebra, and we don't really get an injection into this space. We really need to get an injection into the Galois orbits. So things get more complicated as the dimensions get higher, but these explicit methods allow us to see exactly what's going on in a very neat way. Now, why are we interested in all of these relations, and where does it lead us eventually? So for this, I need to tell you a little bit about L functions. So in the case of classical modular forms, these spaces of classical modular forms also admit Hecke operators. And there is again a basis of simultaneous eigenforms. And if one takes a classical eigenform with Q expansion with coefficients an, one can use it to form a holomorphic function with variable s, a Dirichlet L function. And the nice properties of these L functions come from the fact that F was an eigenform. So the fact that F is an eigenform and these Hecke operators commute tell us that the coefficients an are multiplicative, which tells us that this L function has an Euler representation as an Euler product, and we can write this Euler product explicitly in this form. And this gives rise to a completed L function, which is written right here, which satisfies a certain functional equation. So this epsilon of F is the sign of F under some operator, which depends only on F. And the point is that these functional equations allow us to continue analytically this L function, which is originally defined only on some right half of the complex plane, to the entire complex plane. And this L function determines, okay, maybe I should say, this continuation of the L function allows us to deduce things we couldn't have deduced otherwise. A good example is the case when the weight is 2. Then Eichler-Shimura tells us that this L function is actually the L function of an elliptic curve. Now, the L function of an elliptic curve tells us things about the rational points on this elliptic curve. So it really is some holomorphic function that has a lot of arithmetic information. And the only reason it can do that is because we have this functional equation and we can continue it analytically. And maybe what's hiding here in the background that I didn't say a lot about is that this L function of the elliptic curve depends on how the Galois group of Q acts on this elliptic curve. Okay, this elliptic curve is just a set of solutions to this equation, say y squared plus y equals x cubed minus x squared. And if we have some solution, then over some number field, then any automorphism of this number field will give us another solution. And the rational points are those fixed by all these automorphisms. So there is a natural action of the Galois group on this elliptic curve, and the L function of the elliptic curve, of course, is actually the same as the L function of the this Galois representation. On the other side, this classical modular form is actually coming from a representation, an automorphic representation of PGL2 on this space, the adelic points of PGL2. And this L function doesn't really depend on F, but on this irreducible automorphic cuspidal representation. So really modularity tells us that there's a bijection or a correspondence between these representations on both sides. And this correspondence is not just a bijection of sets. There's also some properties that are preserved between the two sides. For example, the Hecke operators on the modular form side correspond to Frobenius acting on the Galois side. Why am I telling you all of this? Well, for Siegel modular forms, in this example for Siegel modular forms of degree 2, we can also associate L functions. Now, the way to do that is slightly less straightforward, and I won't introduce it here. But by looking at the relevant automorphic representation, one can again produce an L function, which can be continued analytically to the entire complex plane. And we conjecture that, for example, if the relevant weight for the Siegel modular form is 3, 0, then this L function comes from certain varieties, certain geometric objects. So in this case, this will be Calabi-Yau threefolds. And in recent work with Ladd, Rama, Tornarea, and Voigt, we use the exceptional isomorphism in the next dimension, in 5 dimensions, that tells us that the orthogonal group of dimension 5 has the same Lie group as a symplectic group of dimension 4, to build a database of Siegel modular forms of this weight and match them up with corresponding varieties, these Calabi-Yau threefolds on the other side. Okay. How much time do I have?
7 minutes or maybe more.
7 minutes. Okay. I will skip a little bit about Langlands parameterization. You know what, maybe, okay, I'll say something about it. So for a modular form, like things on the left side here of this modularity, we can parameterize them in a very nice way, following work of Langlands. And the idea is that we have a parameter at every prime p and one parameter in infinity. These parameters give us conjugacy classes of elements in 2x2 matrices. And these are called Satake parameters. So for example, if we had a classical modular form, then we could write the eigenvalues of its Hecke operator after normalization as the sum of some element and its inverse, some alpha p. And then the diagonal, the semi-simple element with diagonal alpha p inverse will be its Satake parameter at p. And similarly, one can write a Satake parameter in infinity, which takes any non-zero complex element into a conjugacy class of a 2x2 matrix over C. Now, these Satake parameters give us a way to classify these automorphic representations over PGL2, but also over larger groups like PGLN in general. And we can construct a set of Satake parameters that gives rise to an automorphic representation of a larger group from PGL2. And the idea is just to use the construction of the symmetric power to give us representations over the larger group. And these representations are usually non-Caspilov. So this corresponds in classical language and terminology to the existence of lifts. We lift modular forms to get modular forms of larger groups. And the reason that our Langlands parameters in this example always live in SL2, or in this generalized case in SL2D, is because this is the dual group to PGL. And more generally, when we have a reductive group, we can dualize the root lattice and get a dual group on the other side. I put here a table for your convenience. Like if we start with the orthogonal group of even dimension, it's self-dual, but if we start with odd dimension, we get the symplectic group. Like A and D are self-dual, and B and C are dual to each other. So a conjecture of Langlands that was refined by Arthur was that if we have some representation R of the dual group, and we start with some discrete automorphic representation, then applying R to the Langlands parameters of our representation, we always get something that looks like it's built from these building blocks, from these extension by symmetric powers of these smaller building blocks. And of course, this conjecture also has a specific description of the image that I would not say much about. And Arthur's classification showed that this is true when G is classical and R is the standard representation. I should say that Arthur only showed it for the split form, and then Taibi in 2019 showed it for other inner forms. Again, only when R is standard. And one could ask what happens when you have R that is not standard, and how does it relate with the zeta correspondence? And this leads to a result I have with Fretwell, Ingalls, Logan, Secker, and Voigt that tells us how these relate to one another through the theta correspondence. So when we have an eigenform in the orthogonal side, so this is an orthogonal modular form, which is an eigenform for the Hecke operators there, and we apply this theta G, that the nice thing about theta G that it is Hecke equivariant, and one can see what it does to the Langlands parameters on both sides. So we have here two cases. And I should say that the case when the lattices are unimodular or the discriminant is 1 was done by Chenevier and Lan. And you can see here an example of how it affects the relation between the L functions. So this relation between the Langlands parameters is directly interpreted as a relation between the L functions. And that gives things like, for example, if G equals 1, we can get an explicit relation between the eigenvalues of these forms. This leads to other interesting results, such as generalized Eisenstein congruences, and one can reobtain Ramanujan's famous congruence this way, but I think I'll stop here.
Thank you very much. Thank you. Eran, questions? Comments? From the audience. Questions? Brian? Okay. In that case, let us thank Eran again for the nice talk.
Thank you.
Thank you.